Hello viewers, I am Kausalya. Today we are going to solve problem number 2 under the topic lag compensator using Bode plot. The problem is the open loop transfer function of a certain unity feedback control system is given by this expression. It is desired to have a phase margin to be at least 33 degrees and the velocity error constant kV is 30-second inverse. Design a phase lag series compensator. So here in the problem you see the given transfer function is a open loop transfer function and the type of feedback is unity feedback. Here the system is desired to have a phase margin of 33 degrees, that is at least 33 degrees. It means that the system should have phase margin of minimum 33 degrees. If it has more than 33 degrees, it is well and good, right? And here an additional information, that is velocity error constant is given. What is the purpose of having this velocity error constant is, with the help of this value we should find the value of k here, right? So if there is a need, then we should design a phase lag compensator, right? If this transfer function gives the phase margin of 33 degree, no need to go for compensation, or else we should do the compensation, right? So the step 1 is calculation of gain k. So here the kV formula is limit s tends to 0 s into g of s into h of s. Here the g of s is given in the problem and the h of s value is 1 because it is a unity feedback. So these two s cancels each other, and when you substitute the value of s equal to 0, finally the value of kV is found to be k by 320, right? Now the value of kV is, it is given, right, it is 30. So when you substitute the value of 30 over here, the value of k is equal to 9600, right? And step 2 is to find the Bode plot of uncompensated system, right? Just now we had find out the value of k. So just substitute the value of k in the transfer function. So here this is our new transfer function, right? Now here I am going to take the constants outside. From this expression I am taking 4. When you take 4 outside, this expression gets modified as s by 4 plus 1, right? Again here when you take this number 80 outside, this term gets modified as s by 80 plus 1, right? So when you take the numbers outside and when you cancel, finally our transfer function is like this: 30 by s into 1 plus 0.25 s into 1 plus 0.0125 s, right? Then the next step is substitute s equal to j omega. When you substitute j omega, this is our expression. So now we are going to find magnitude plot and phase plot, right? So to find the magnitude plot, first step is we have to calculate the corner frequencies. How to find corner frequencies? We have to take the reciprocal of the coefficient of j omega. Here coefficient of j omega is 0.25 and here coefficient of j omega is 0.0125. Just we have to take the reciprocal. So once you take reciprocal, the values are 4 and 80, right? 4 is minimum, so here it is given omega c1, and next is 80, so it is omega c2, right? The next step is we have to form the table. So how to form the table? We have to arrange the constants in this order, that is, the first place will be occupied by number along with individual omega term. So when you look at this transfer function, here I am having 30 by j omega, right? So just write it over here. And next is we have to arrange the terms based upon the ascending order of corner frequency. So here 4 and 80 are the corner frequency. So the 4 is contributed by which term? 4 is contributed by this 0.25. So we have to write this term 1 divided by 1 plus 0.25 j omega, and similarly the next is 80 is contributed by this term. So here we are writing expressions, okay, terms like this. Then since we are having j omega in the denominator, this contributes a slope of minus 20. Since omega lies in denominator, here minus is included. Likewise here also omega lies in denominator and here also. So minus 20 and minus 20. And the next is change of slope. So how to calculate change of slope? You see, whenever there is corner frequency, then automatically there will be change of slope. So the constant term won't contribute any change of slope, so just we can leave it. So here this minus 20 is moved downwards and this minus 20 is shifted to the right side. So minus 20 gives you minus 40, right? And now again this minus 40 is shifted downwards, and again we are moving this minus 20 to the right hand side. So minus 40 minus 20 gives you minus 60. In case if you want to know about the Bode plot in detail, kindly refer to the previous videos where I have solved many problems in Bode plot. Okay, there maybe I can explain much more in detail in those videos, so kindly check it, right? The next step is, here we have to select two frequencies. One is known as omega L, that is lower corner frequency, and next one is omega H, that is higher corner frequency. Here what is the value of omega C1? Here the value of omega C1 is 4 and the value of omega C2 is 80. Right. So we have to select a value which is less than this 4. So here we had selected 1. And here omega H should be greater than this 80. So here it is selected as 100. Even you can select 200, 500, whatever may be. It won't make any difference. Okay, the final answer will remain the same. So next one is calculating magnitude. So magnitude is given by mod of j omega in decibel. Since we are representing magnitude in decibel, you see here 20 log is included, right? So for the first two frequencies, for omega L and omega C1, we have to consider only constant with individual omega terms. So here from the transfer function, the constant is 30 by j omega, right? Wait, let me show you. You see, this is our transfer function, right? So here this transfer function has constant with individual omega term. Omega lies in denominator. So here we are considering 30 by j omega. So here initially the value of omega L is 1, right? So just substitute it over here and the answer is 29.5. We are rounding it off, that is 30 dB. And at omega equal to omega C1, right? Again the value of omega C1 is 4. So just substitute and find out its value. It is 18 dB. And next one at omega equal to omega C2. So here just this is like a formula. So change of slope from omega C1 to omega C2 into log of omega C2 by omega C1 plus the value of A when omega is omega C1. Right, so change of slope from omega C1 to omega C2 is, that is from the table, just you can refer, it will be minus 40, right, into log of, we know omega C2, omega C1 and the value of A when omega equal to omega C1, you see. At omega equal to omega C1, the value of A is 18 dB. So just substitute it and find out the answer, it is minus 34 dB. And the next one is at omega equal to omega H. Again here the formula gets modified as change of slope from omega C2 to omega H into log of omega H by omega C2 plus the value of A when omega equal to omega, here it is omega C2, right? So from omega C2 to omega H, the change of slope is, you see, this is our omega C2, right? And omega H will be next to it, right? Because it is the next higher value. So change of slope from omega C2 to omega H is, again here this minus 60 will occupy a place over here, right? So change of slope is minus 60. So minus 60 into log of, again omega H is 100 and omega C2 is 80 and the previous value is minus 34, right? So the final answer is minus 40 dB. Here I had made a simple tabulation of omega and magnitude, right? It will be easy for us to plot in a semi-log sheet. And the next one is calculation of phase plot, right? So this is our expression, right? A constant term won't contribute any phase angle. So omega in denominator contributes 90 degree. I am going to shift these three terms to the numerator, so a minus is included. So omega contributes 90 degree. As I am moving this to the numerator, minus 90. And again here the general format is tan inverse of imaginary coefficient. Here imaginary coefficient is 0.25 divided by the real term is 1, right? So 0.25 omega by 1 and here 0.0125 omega by 1, right? And next again we have to find different values of phase angles for different omega values. So it is must to include the values which we considered for magnitude. For magnitude we have taken 1, 4, then 80 and 100, right? Even you can take between values also. So here you see 4 and 10 are included. If you have a minimum of some 7 to 8 values of omega, then the phase plot will be much more easier to draw, right? That is the reason. So here substitute omega equal to 1 in this expression, write down its value. Likewise you have to do the remaining values of omega and you have to find out the phase values, right? The next one is calculation of phase margin of uncompensated system. So prior to this, we have to draw the values, that is magnitude plot and phase plot on a semi-log sheet. Wait, let me show you. So this is our semi-log sheet, right? Here I have taken values as 0.1, 1, 10, 100 and x-axis stands for omega, right? And one side of y-axis stands for magnitude and other side of y-axis stands for the phase angle, right? So select the values, depending upon the values we get for magnitude and for the respective phase angle, right? So after writing the values, it is must to write the scale, right? So now we are going to draw the magnitude plot first, right? So what are all the values we have? You see, when you again look back at the table, for when value of omega is 1, the magnitude is 30. So here the value of omega is 1, right? So the magnitude is 30. So here you see 10, 20 and 30. So I had marked point here. Likewise, when the value of omega is 4, magnitude is 18. So here you see, this is my 1 and this is my 10. So between 1 and 10 lies the 4. So you can move like this, 1, 2, 3, 4. Okay, at 4, the magnitude is 18. So here I had marked 18, right? Likewise, you just plot the remaining points and by using scale, you have to draw the phase plot. Initially, you have to join these 2 points and then these 2 and finally these 2, right? Wait, let me draw and show you. So you see, this is our magnitude plot, right? And you have to always highlight this 0 dB line, right? It is must. Then next, I am going to draw the phase plot. So I had already marked the points over here. So regarding phase plot, it should be joined by using our free hand, right? Wait, let me draw and show you. So finally, this is our magnitude plot and this is our phase plot, right? So the next thing is we have to calculate the phase margin. Okay, so how to calculate the phase margin? You see, our magnitude plot intersects 0 dB line at a particular point. From this point, just draw a line downwards till it meets our phase plot. At particular point where it meets our phase plot, just measure the angle. Here it is equal to minus 168 degrees, right? Kindly make a note of it. Step 3 is calculation of phase margin of uncompensated system. So just now we had find out the value of this pi GC as minus 168, right? So substitute that value in this formula. Even we can it is from Bode plot. Okay. From Bode plot, this value, we are getting this value, just substitute it and the answer is 12 degrees. But what is the expected value? The value which is given in the problem is 33 degrees, right? So we are going for a lag compensation, right? And the step 4 is choose a suitable value for the phase margin of compensated system. That is, the phase margin value is given as gamma n is equal to gamma d plus epsilon. Gamma d is the desired phase margin, that is the value which is given in the problem. So it is 33 degrees plus, initially we have to select this value of epsilon as 5 degrees. So when you substitute it, the answer is 38 degrees, right? So the next step is, step 5 is determining the new gain crossover frequency. So again, the formula is gamma n is equal to 180 degree plus pi GCN. So pi GCN is given as gamma n minus 180. The value of this gamma n is 38 degrees. So just substitute it over here. and finally the angle is equal to minus 142 degrees, right? So keep this in mind. We have to again move to our semilog sheet. You see the angle is minus 142, right? So here minus 140 and the next line is minus 144. So just let me place a dot in the middle, right? Now I have to draw a line from this dot to the phase plot, right? Wait, let me show you. You see here I had drawn the angle is that minus 142. From that minus 142 we are just drawing a line. It meets the phase plot at a particular point, right? Just you have to measure the value of omega at that point, okay? Just draw a line. So here the value of this omega GCN is 4.7 radians per second, right? Here you see, just make a note of it. This is your new gain crossover frequency. It is 4.7. Again, this is we are getting from the Bode plot, right? The next step is determine the parameter beta, right? So here, oh sorry, I forgot to tell. Again, for that respective frequency of 4.7 radian per second, you just again extend the line and find the respective magnitude. Wait, you see, we had find out the value as 4.7, right? So from this point again, you just extend the line such that it meets your magnitude plot, right? It will meet the magnitude plot at a particular point. Just measure the value at that point, okay? Just measure the respective magnitude value. It is equal to 16, right? So make a note of it. So that is why here you see magnitude is 16 dB, right? So the formula here is AGCN, that is the magnitude at the new gain crossover frequency is 16 dB. Since it is in dB, you see here we are writing it as, sorry, the another formula for this magnitude is 20 log beta, right? Now we are going to equate these two terms because this is also magnitude and this is also magnitude. So when you equate, the value of beta is found out to be 6.3, right? The next step is determining the transfer function of lag compensator. So here the zero of the compensator is just given by, okay, this is the formula, you can keep this in your mind. Zero of the compensator is given by 1 by t as well as omega GCN by 10, right? So from this the value of t is just you have to take the reciprocal. So it is 10 by omega GCN. We know the value of omega GCN, right? It is 4.7. Just substitute and find the value of t. The next one is pole of the lag compensator. So this is given by 1 by beta t. So the value of beta just now we had find out, right? It is equal to this 6.3. So just substitute. We know what is beta and what is t and find out the value of this pole. It is 1 divided by 13.419, right? And the transfer function of lag compensator is given by this expression. Just take LCM. When you take LCM and rearrange, we will be having expression like this, right? Now substitute the values. We know what is beta, we know what is t and what is beta into t. So just substitute it and finally this is our transfer function of the lag compensator, right? And step 8 is determine the open loop transfer function of the compensated system. So for the compensated system, when you look back at the procedure, we will be having a block diagram similar to this, right? So here, this is the given transfer function. That is the transfer function which is given in the problem, right? Just we have substituted the value of k by 30. That's it. The remaining things remain the same. And this is the transfer function of your lag compensator and this is nothing but 1 by beta, right? So how to find the open loop transfer function? Here we are having these three blocks connected in series. So just we need to multiply. So when you multiply, the common terms get cancelled and finally the transfer function occurs like this, right? And the next one is determining the actual phase margin of the compensated system. Now a compensation is done. And now we are going to check whether this system has a phase margin of 33 degrees. So what is the procedure? Again replace S by j omega and write down an expression for phase angle. right? So the phase angle expression is given by tan inverse of imaginary coefficient divided by the real term. So tan inverse of 2.13 by 1. We are having only one term in the numerator, right? So we had written that. Next one is omega gives 90 degree. Since it lies in denominator, it is minus 90. Likewise, write down the expression for the remaining 3 terms, right? The next thing is, at omega equal to omega GCN, the value of pi naught is equal to pi GC naught, right? So here we are doing nothing, okay? Don't get confused. So only didn't explain the terms that pi naught, pi GC naught and all. Just write down the expression, right? This G naught includes, this is a open loop transfer function of a compensated system. That's it. Keep that one in mind, okay? The next thing is, here in the place of omega, we are replacing omega GCN because this is our new gain crossover frequency, right? So just substitute the values accordingly and find out the value of pi GC naught. It is equal to minus 147. So from this, again, the phase margin expression is 180 plus pi GC naught, right? So this pi GC naught is given as minus 147. So just substitute the value over here and the phase margin is found out to be 33 degrees. Right, so this is the desired phase margin which is given in the problem. So our lag compensator device had meet the desired specifications, right? So in conclusion, the actual phase margin satisfies the requirement. That's it. And the result, here you have to mention the transfer function of lag compensator as well as transfer function of lag compensator system. So here, this is the transfer function of your lag compensator, right? Again, just we are simplifying, we are bringing it to the standard format. That's it. Here I am taking 2.13 outside. Here also 13.419 outside. So when you simplify, we will be getting expression like this. And the next one is transfer function of lag compensated system. So just now we had find out, right? Just in the result, you have to include these two transfer functions, right? That's it. I hope you people understand the problem. If you have any doubt, let me know in the comment section. Thank you.